So today's topic is potentiometer. So first of all, we have to know what is a potentiometer. So basically, it is a electrical instrument that we generally use to measure EMF, or to compare EMF, okay, and we also use it to measure the internal resistance of cells. And in previous class already we discussed about meter bridge, right? So meter bridge is also an electrical instrument where 1 meter long wire is used, but in potentiometer generally we use wires of larger or longer length. Suppose the potentiometer that we use in our lab, there we are using 10 wires, each of length 1 meter, so total length is approximately 10 meter. All right, now the question is that if the wire is of 10 meter length, how we will manage it, because it is not a small length, right? So you can see this figure, this one, how we arrange this wire. See, this point A is the starting point of the wire, then the wire goes like this, okay, and then there is a metal strip. With the help of this metal strip, a next part of the wire is connected. So this is 1 meter, this is another 1 meter, so that is 2 meter. Then again with one metal strip, next part is connected, so this is again another 1 meter, so 3 meter. Next metal strip, this one, okay, with that another 1 meter, so 4 meter. So in this diagram I have drawn a potentiometer of 4 meter length, but in our lab the instrument that we use, that is a potentiometer with 10 meter length, okay. So in this way we arrange the wire. Now the main thing is the working principle. What is the working principle of potentiometer? Okay, so first of all let us start with Ohm's law. Here you can see I have written V equals to IR. Now V will remain as it is, I will remain as it is. In place of R we can write rho L by A. We already got this formula for resistance. And from this equation, suppose if a constant current flows through a circuit or through a wire, that means I will be constant, and if the wire is of uniform cross section, then A will be a constant, and rho is already a constant, right? So what is the variable here? The variable is only L, okay. So that means we can say that V is proportional to L, or V is equal to KL, where K is a constant, and this constant is called potential gradient. We will discuss about it later on, but this is the working principle. Or on this formula the working of this potentiometer depends. V is equal to KL, that means potential difference across any conductor depends on its length, okay. More the length, more is the potential difference. Suppose here there is a battery, this one is a battery, okay. This battery is connected across a wire, this AB, there is a wire, and the battery is connected across this wire. So if you measure the potential difference between point A and point B, how much you are supposed to get? That will be equal to the potential difference of the that created by the battery, which is V here, okay. So across AB the potential difference is V. So if I consider any length, suppose C, then what will be the potential difference? Suppose this length AB is equal to L, and the length AC is equal to X. So how we will do that? How we will get the potential difference across point A and C? So for that we can use this formula. Alright, how we can use it? Suppose if L length is having V potential, then by unitary method, unit length will have how much potential? Unit length will have how much potential? L length is having, L length is having V potential, unit length 1 meter or centimeter, that will have how much potential? V by L. So V by L is nothing but potential per unit length, and if V by L is potential per unit length, means unit length is having a potential of V by L, then X length will have how much potential? V by L into X. So that is the potential difference across point A and C, okay. And we know that V by L is nothing but K. From here you can see, if you divide V by L, what we are going to get? K. So K is, as I told you, K is known as the potential gradient or potential per unit length. Okay, so in that way we can find out potential across any length once we know the length. Alright, okay, then as I already told you that this potentiometer, it is a device which is used to compare EMF or measure EMF or internal resistance. First we will see the application number 1, which is how to compare EMF of cells. Okay, so for that I have drawn this kind of circuit. You can see the circuit is drawn already in your book. That is the main source of battery, and as I told you that this long potentiometer wire, it starts from A, it ends at B, and across this point A and B there is a potential difference or potential drop will be created by this battery, and that potential will be V. Alright, so V is the potential across point A and B. Fine. Now this is the main circuit, but we have one extra circuit also. So that extra circuit starts from this point A. You can see here these are primary cells, small cells. Okay, these two primary cells are connected with point A. The positive of this cell and this cell are connected at A, and the positive of the main battery is also connected at A. Okay, and you can see that both these points, they are this E1, this point C is connected with E1, point D is connected with E2, and point E is connected with a galvanometer, and this J is called jockey. Okay, in meter bridge I told you about jockey. So what is the purpose of this galvanometer? It detects current flowing through, it detects the presence of current flowing through it. Okay, now suppose this is called a two-way key. Two-way key. Two-way key. Okay, fine. Now this two-way key, what is the function of it? Suppose if you join point C and E, D is not in the circuit, then obviously this cell E2 will not be there in the circuit. Okay, and once you join or connect D and E, then point E1 will not be there in the circuit. So separately we will connect once, first time E1 in the circuit, in the main circuit, and then for the next time we will connect E2, and that is why we use a two-way key here, with the help of which we can connect only one cell at a time. Okay, now suppose E1 is connected with the galvanometer by connecting C with E. Alright, now this jockey, we will slide the jockey, we will start sliding the jockey from point A towards B. First we will keep the jockey at A, then we will slide it like this, then through this wire this way. And suppose when the jockey is at position J, the galvanometer is showing zero deflection, null deflection. Okay, so what is the meaning of showing null deflection? Because nothing or no current is flowing through the galvanometer, that is the meaning, right? Now why no current is flowing through the galvanometer? What is the reason? No current is flowing through the galvanometer means one thing is clear, that no current is flowing through this part of the circuit, but current is flowing through this part, through the meter bridge wire current is flowing. This key should be closed. Okay, this key should be closed. Okay, so why no current is flowing through this part of the circuit, through the galvanometer? The reason is that we know that current always flows from higher potential to lower potential. So the only possibility for which the current is not flowing to the galvanometer is that the potential difference created in this part of the circuit will be equal to the potential drop across point A and J. There is no potential difference actually. They are in equal potential. Means suppose just now I told you, right, that across AC, if you want to find out the potential, that will be K into X. So if I want to find out the potential across AJ, instead of AC I have written AJ. So what will be the potential difference? K into k into, just like this, k into what, the total length, how much length is that. So this length, suppose from a to j, this a to j, the length is L1. So what will be the potential difference across these 2 points a and j? That will be simply k into L1, because L1 is this length, aj length is L1. So potential drop across a and j will be this much, k into L1, and this potential drop means k into L1, that should be equal to the potential difference created by this part of the circuit by the cell, which is E1. E1 is the EMF or potential difference created by this cell in the circuit. Okay, correct. So that means what, KL1 should be equal to E1, means between AJ point, whatever is the potential difference, the potential in this part of the circuit is also same. So that is why no current is flowing through this part of the circuit. So for that, what equation we will write? KL1 is equal to E1. But one important thing, here I have taken the EMF of the cell, or EMF of this cell, not the potential difference. Already in previous classes we discussed about EMF and potential difference. There is a small difference between both, right? So EMF means that is the potential difference across a cell when no current is drawn from the cell. Now see, as I told you that in this circuit nothing is there, no current is there, so certainly what we are going to get across, what we are, if you measure, what we are going to get, that is EMF, not potential difference. But yes, in case of, suppose when current flows through this circuit, or when current is drawn from this circuit, then that will be potential difference, not EMF. But this time, since no current is flowing through this part of the circuit, this will be EMF. So that is why EMF E1 of this cell is equal to potential drop across point AJ, which is KL1. And how we got this? We got it from this formula. Alright, so this is for cell E1. Next step, now we will open this C and E connection, then we will connect D with E. So which cell will come there in the circuit now? E2. And suppose for E2 we will again do the same procedure, that means this jockey will again, we will slide it from A to this side, and when the jockey is at J dash, suppose, then this galvanometer is, suppose again it is showing 0 deflection. So this time again same procedure, the length AJ dash, which I will take as L2, this L2 this time will be equal to what? E2, means KL2 will be equal to E2. That's what I have written in the next page. Here I have written, okay, for the next cell KL2 is equal to E2, and once you take the ratio, L1 by L2 is equal to E1 by E2. Now there I told you that this potentiometer is used to compare the EMF. So see here, since it is a ratio of both the EMF of both the cells, so it is comparing the EMF of both the cells. And L1 L2 can easily be measured from the instrument itself, because it is a length, and to measure length with the instrument there will be a meter scale attached to it. So with the help of that meter scale we can easily measure L1 L2. And suppose out of this cell E1 and E2, if one EMF is known to us, then the other EMF we can easily find out. So there in the last page, means here I have written that this one, that potentiometer can be used to measure EMF. How to measure the EMF? If the EMF of one cell is known, then we can measure the EMF of other. But if the EMF of both the cells are unknown, then we can compare the EMF. Okay, and the next one is how to find out the internal resistance. So for that again we have another circuit, this one, point number 2, how to calculate the internal resistance from potentiometer. So for this, you see the circuit, here we have taken only one cell, which is E, okay, this cell, and this cell, it has an internal resistance of R, small r, and capital R is the external resistance connected to it. And in this small circuit we have a key K dash, and in the main circuit we have one key K. Okay, now first step of the experiment, first we will open this K dash. Once we open it, that means no current will flow through this part of the circuit, right? That means in other word, no current will be drawn from this cell E, because this key is open. So once no current is drawn from the cell, what we are supposed to get? EMF of the cell, not potential difference. So suppose when this K dash is open, this part of the circuit does not exist, only this part does not exist because K is open. So only what we have this part, as we got in the previous experiment. In previous experiment there were two cells, but we connected one only at a time. So here one EMF, one cell is connected with the internal resistance, with galvanometer and tilt jockey. So this part is same with the previous one. Okay, then what should we do? We will slide the jockey from point A to this side, and at a particular point we will get the null point, and suppose the point is J. So just like the previous one, and this length AJ is, suppose it is L1. So like previous case, how we wrote there E1, because there were two cells, but here we have one cell, so we will write it by E only. So E will be equal to KL1. This is given equation number 1. Okay, next case, this K dash is closed now, and once K dash is closed, what will happen? Current will be drawn from the cell E. Okay, so this current which will be drawn from cell E, this current will flow in this direction, in this small loop. Okay, it will keep on flowing like this. So this current will be confined within this small loop, but since the current is drawn from this cell E, this time the value that we are going to get, that will not be the EMF of the cell, but that will be the potential difference across the cell, which will be given by V. Okay, so by closing this K dash, again the same procedure will be followed. This jockey will be shifted from A towards this, and at a particular point, suppose at J dash, where J dash is this point. Okay, it should be less than J. So this at J dash we are getting the zero deflection in the galvanometer. So what should we write now? And suppose AJ dash, this length is L2. So for the second case we will write it like this: KL2 is equal to V. This time we are not going to write E, because current is drawn from the cell and we are getting potential difference and not EMF. So this will be V. Okay, then 1 by 2. 1 by 2, if you do, we will get L1 by L2 is equal to E by V. Okay, where L2 will be less than L1. The reason is that V is what? V is less than E, right? So that is why L2 will be less than L1. This condition you remember. Then E means we can write I into R plus R. If you remember, while discussing about the combination of cells, you got this formula, I think. It was this one, no? Current, yeah. Current I is equal to, it was E by, means EMF by capital R plus small r. Capital R was the external resistance, this is the internal resistance. So if you cross multiply, E will be equal to what? I into R plus R. Okay, so that's what I have written here. In place of E, I have written I in. So in this place, here I into R plus R I have written. Alright, I into R plus R. Okay, then in place of V, since V means it is the potential difference, and potential difference is not related to internal resistance of a cell. So from Ohm's law we will write, in place of V we will write IR. Alright, and once we write this, I will get cancelled, and this will be small, just to the division, small r by capital R plus capital R by capital R. If you divide, it will become 1. Alright, now this R by R, this L1 by L2 will remain this side, 1 will go that side, it will become minus, and here we will have small r by capital R, and finally small r equals to this. So this is the formula with the help of which we can calculate the internal resistance of a cell, because you see here this capital R will be a known resistance which will be connected here. Okay, and L1 L2 can easily be measured with the help of meter scale attached to this potentiometer. So we can easily find out the value of internal resistance of the cell. Okay, then one very important point, one question is there: why do we prefer potentiometer over voltmeter to measure EMF of a cell? Very important topic or important question. I'll tell you the answer, but you will write it by yourself. Okay. See here, why do we prefer a potentiometer over a voltmeter to measure EMF of a cell? Suppose if we take a cell like this, okay, this one, and if you connect a voltmeter across it to measure the EMF, suppose, how we will connect the voltmeter? Like this, we will connect the voltmeter here, okay. So if you connect the voltmeter, certainly some amount of current will be drawn from the cell, like this way, since it is getting a path to flow. So if certain amount of current is drawn from the cell, certainly we will not get the EMF of the cell, but what we are getting is the potential difference, which is not our requirement. What we are supposed to find out, EMF of a cell. So that is why voltmeter is not ideal to measure the EMF of a cell. Once we connect the voltmeter, it actually measures the potential difference. But yes, potentiometer can give us the accurate value of EMF. The reason is that when we get the null point, no current flows through the galvanometer. So that means no current is drawn from these cells, and since no current is drawn from the cells, we are getting directly the EMF of the cell and not the potential difference. So this much for today, and we have already completed all the chapters from this all the topics from this chapter. So in next class we will start the new chapter, which is semiconductor, from volume 2. Okay then, thank you.